This is Beyond the Business.
When we talk about water, we almost always talk about drinking water. Clean water, access to the water, shortages, human health. Water is described as a vital resource, a basic human need, something that must be protected because people depend on it. And all of that is true. But it is only part of the story because the largest volume of water used by modern civilization is not used for drinking at all. It is used as a technical resource. Water that cools power plants, water that washes, dissolves, carries, and transports, water that absorbs heat, chemicals, nutrients, and waste, water that makes industrial scale possible. This water rarely appears in public conversations. It does not show up in everyday life. It exists in permits, processes, and infrastructure plans, not in the headlines. And yet, this is the water that quietly connects industry, agriculture, rivers, and oceans into a single system. In this episode, I'm not talking about accidents or spills. I'm talking about normal operations, about how water becomes a working fluid for the economy, how it is used, altered, and returned, and how rivers and deltas slowly shift from ecosystems into transport corridors for toxicity. Welcome to the ocean of waste. Agriculture is the largest user of fresh water on the planet. Roughly 70% of global freshwater withdrawals go into agriculture, and the vast majority of that water is used for irrigation. This alone already changes how water should be understood. It is not a marginal input, it is the backbone of food production at scale. Economically, this logic is straightforward. Water enables higher yields, predictable harvests, and industrial scale farming. Irrigation allows agriculture to expand beyond natural rainfall limits, turning land into a controllable production system. Fertilizers and pesticides complete that system by stabilizing output and protecting crops against uncertainty. From a business perspective, water is not consumed. It is used to deliver productivity. But environmentally, this same mechanism creates a very different outcome. Irrigation water does not disappear, it moves. As water flows across fields, it collects nitrates, phosphates, pesticides, and chemical residues from fertilizers and soil treatments. Part of this mixture infiltrates groundwater. Another part drains into nearby streams and rivers. Over the time, entire river systems become transport corridors for agricultural chemistry. This process is gradual, continuous, and largely invisible. One of the most studied examples in the Mississippi River Basin in the United States. Decades of intensive agriculture across the Midwest have led to massive nutrient runoff into the river system. These nutrients travel downstream and accumulate in the Gulf of Mexico, where they fuel large scale eutrophication. The result is one of the world's largest recurring dead zones, covering thousands of square kilometers each year. The key point is not the size of the zone, but its origin. The pollution is not coastal, it is continental. Another well documented case is the Po River Basin in Italy. The river drains one of the Europe's most productive agricultural regions. Fertilizers and agricultural runoff move steadily into the Adriatic Sea, where nutrient accumulation has repeatedly triggered algae blooms, oxygen depletion, and ecosystem stress in coastal waters. Again, there is no single event to point to. The system works as designed, and the consequences appear slowly. A more recent and particularly revealing example is the Mar Menor lagoon in southeastern Spain. Mar Menor is a shallow, semi enclosed coastal lagoon connected to the Mediterranean. For decades, intensive agriculture expanded across the surrounding region, supported by large scale irrigation and fertilizer use. Nutrient-rich runoff from fields entered groundwater and drainage systems, eventually flowing into the lagoon. For years, the system appeared stable. Then the accumulation crossed a threshold. Massive algae blooms consumed oxygen, light penetration collapsed, and large-scale fish die-offs followed. What made Marminor especially striking was that there was no industrial accident, no sudden spill, no failure of infrastructure. The lagoon degraded under fully permitted agricultural activity operating exactly as planned. Marminor did not fail because something went wrong, it failed because nothing stopped. This is what makes agricultural water pollution structurally difficult to address. It is not caused by malfunction, it is caused by normal operation. Each individual farm operates within permitted limits. Each application of fertilizer is justified locally. But ecosystems don't respond farm by farm, they respond to cumulative load. The risk here is not immediate toxicity, it is systemic transformation. Nutrient-rich water alters oxygen levels, changes microbial activity, and reshapes food webs. Once eutrophication patterns are established, they are extremely difficult to reverse, even if inputs are reduced later. The system does not reset quickly and remembers. This creates a delayed feedback loop. Agricultural productivity improves in the short term. Water quality degrades downstream over decades. By the time the signal becomes visible in the coastal waters, the source is diffuse, distributed, and politically difficult to address. What makes this risk especially critical is scale. Agriculture operates across entire continents. Rivers connect that scale directly to the ocean. The ocean in this system is not exposed to agriculture directly, it receives its consequences. And because those consequences arrive slowly, continuously, and without a clear point of failure, they are often recognized only when the system has already crossed the threshold. And this is not a failure of farming, it is a failure of how water is treated within the agricultural model. Water is managed as a productivity tool, its downstream role as a chemical carrier is secondary. And that is why agriculture sits at the core of the poison narrative. After agriculture, energy is the second major sector where water quietly carries the weight of the system. Globally, the energy sector is one of the largest industrial users of fresh water, particularly in the countries with large thermal power fleets. Coal, gas, and nuclear power plants all depend on water for cooling. Without it, stable electricity generation at scale is not possible. From an economic perspective, this is efficient. Water allows power plants to operate continuously, safely, and at high output. It stabilizes temperature, protects equipment, and enables dense energy production close to demand centers. Rivers, lakes, and coastal waters become integral parts of the energy system, not as ecosystems, but as cooling infrastructure. In many regions, energy production would simply not exist without access to large volumes of water. But again, water does not leave the system unchanged. Cooling water is typically returned to rivers, lakes, or sea. Formally, this is often treated as reuse rather than consumption. The volume remains, the system appears balanced. What changes is temperature and chemistry. Thermal discharge raises water temperatures locally and downstream. Even small increases can significantly reduce oxygen solubility, alter metabolic rates of aquatic organisms, and shift species composition. Fish adapted to narrow temperatures. Ranges are forced to migrate or die off. Algae growth accelerates. Seasonal patterns become distorted. This effect is well documented in river systems with dense power generations. In parts of Central and Eastern Europe, river temperatures downstream of thermal power plants have repeatedly exceeded ecological thresholds during heat waves, leading to fish kills and emergency shutdowns. In France, nuclear plants along major rivers have faced operational constraints because returning warm water during droughts and heat events would push ecosystems beyond legal limits. Along coastlines, the effect is less visible but more persistent. Coastal power plants release warm water into semi enclosed seas, where circulation is slower and heat accumulates. Over the time, this contributes to chronic thermal stress rather than acute events. Again, there is no single moment of failure. The system functions normally while the baseline shifts. Energy production also introduces chemical pressure. Antifouling agents, corrosion inhibitors, and treatment chemicals used in cooling systems enter the water in trace amounts. Individually, these substances often meet regulatory standards. Collectively, they add to the chemical load moving through rivers and into the ocean. The risk here is not toxicity in the classic sense, it is thermal and chemical drift. As energy systems scale and climate variability increases, water bodies are asked to absorb more heat at precisely the moment they are least able to do so. Droughts reduce flow, heat waves raise baseline temperatures, cooling margins shrink. The system becomes fragile without appearing broken. Energy is produced inland, heat and altered water chemistry move downstream. Rivers deliver these changes to estuaries and coastal waters where they combine with agricultural runoff and urban discharge. The ocean does not see the power plant, it receives the thermal and chemical imprint of energy production. Energy does not poison water in a dramatic way, it warms it, alters it, and returns it year after year. And because heat dissipates slowly in large bodies of water, the ocean becomes the final sink for thermal imbalance. This is not a malfunction, it is how the system is designed to work. If agriculture turns water into a carrier of nutrients and energy turns it into a carrier of heat, industry turns water into a carrier of chemistry. Industrial activity relies on water not as a background element but as an active component of production. It is used to dissolve, wash, cool, transport, and separate materials. In many sectors, water is not optional. It is what makes industrial scale possible. Globally, industry accounts for roughly 20% of fresh water withdrawals, but this number hides a critical detail. Industrial water use is highly concentrated. It clusters around specific river basins, coastal zones, and industrial corridors, where multiple sectors operate side by side. Chemicals, metals, textiles, paper, pharmaceuticals, mining, refining all depend on water in different ways. Economically, this logic is efficient, but water allows processes to run faster, cheaper, and at higher volumes. Rivers and coastal waters become extensions on the factory floor. Once again, the water that leaves the system is not the water that enters it. Industrial water carries residual chemicals, heavy metals, organic compounds, and processed byproducts. Even after treatment, trace substances remain. Individually, they may fall below regulatory thresholds. Collectively, they form a persistent chemical background moving through rivers towards the sea. One of the clearest historical examples in the Rhine River. For decades, the river functioned as a transport corridor for industrial discharge across multiple countries. Chemical plants, refineries, and manufacturing hubs along its banks released treated and untreated effluents into the system. The Sandoz chemical spill in 1986 made the problem visible. But the spill was not the core issue. It revealed how much chemical pressure had already accumulated through normal operations. Even after major cleanup efforts, residues continued to move downstream into the North Sea. A similar pattern is visible today in parts of East Asia. The Yellow Sea receives runoff from some of the most industrialized and densely populated regions in the world. Rivers carry industrial effluents, agricultural nutrients, and urban wastewater in the semi-enclosed basin with limited water exchange. Over the time, eutrophication, hypoxic zones, and chemical contamination have become chronic features of the system. No single facility caused this, no single permit failed. The water simply transported everything it was given. The risk here is not acute poisoning, it is a chemical persistence. Many industrial substances bind to sediments, accumulate in organisms, and move up food chains. Once embedded in riverbeds, in coastal sediments, they become part of the system's long-term memory. Each discharge is assessed independently, each substance is evaluated in isolation. But ecosystems experience mixture, interactions, and cumulative exposure over time. The ocean does not distinguish between sources, it receives the combined chemical output of entire industrial regions. Industry does not poison the ocean directly, it feeds rivers with altered water, and rivers deliver the result. Water makes industry possible, industry changes water permanently, and the ocean is where those changes finally settle. There is a pattern I keep coming back to this season because it shows up everywhere once you start looking for it. We live inside systems that feel stable. Food arrives and electricity works, factories run, ports operate, agriculture scales, industry scales, the economy keeps moving. From the outside, it looks like continuity. But inside that continuity, something is structurally broken. The broken part is not technology, it is the way responsibility is designed. Society pays to measure the condition of water. Public budgets fund monitoring, agencies, universities, laboratories, river sampling, basin reports, coastal observations, data systems. At the same time, the load is created by the normal operation of private activity. Not always by accidents, not always by scandals, but everyday permitted economically necessary work. Agriculture uses water to drive yields, energy uses water to remove heat, industry uses water to dissolve, wash, carry, separate, and scale. The water leaves those systems altered, and the ocean receives the result. So we end up with three roles that don't connect into a single chain. The public pays for measurement, private systems generate pressure, ecosystems absorb the consequence. And between those three, the management loop is missing. That is why measurement so often does not become control. Because measurement is treated as the final step. It becomes proof that we are aware, it becomes documentation that something is happening, it becomes a report that can be filed. But it does not automatically trigger action. It does not force a reduction of load, stop expansion, change permits, or reshape business models. So the data exists, but it does not govern. And this is where ownership disappears. A company can say it follows standards, it can publish a sustainability report, it can describe processes, intentions, and targets. But that report is usually built around what is easy to report and what is safe to publish. It often speaks about efficiency and compliance. It often avoids the uncomfortable part. It rarely shows what water becomes after it passes through the system. It rarely connects upstream use to downstream consequence. It rarely owns the cumulative load of a river basin. And it rarely owns what happens in the delta, the bay, and the coastal sea. So the report can look clean while the ecosystem becomes weaker. This is not always deliberate deception. Often it is structural. Because reporting describes a company boundaries. Water does not respect boundaries. A river does not care about permits, a delta does not care about industry categories. The sea does not care which company discharged which molecule. The system only feels the total load, and the state sits in an uncomfortable position where the government monitor, governments aggregate data and sometimes publish it. But converting the data into hard limits is politically difficult. It is economically sensitive and forces visible trade offs. It forces someone to say openly that a region is under pressure, that a basin is degrading, that expansion has a cost that cannot be hidden. So even when knowledge exists, the decisions remain cautious, delayed, and fragmented. And the public remains outside the loop. People don't receive real time signals, they don't get simple local indicators on a phone, they don't get a clear warning that the river is stressed today, they don't get a public map that says this zone is under influence and this is what it means. Information exists, but it stays inside reports and institutions. Because once information becomes live, it demands choices. It demands constraints, accountability, a shift in how the economy behaves. So the system stays quiet, and that silence makes the problem worse, not better. Because these are slow systems. Water carries residues quietly. Nutrients move downstream season after season. Heat accumulates in semi enclosed waters, and chemical traces bind to sediments and persist. So the feedback is delayed. By the time society sees the result clearly, the source is diffuse. It is distributed across thousands of actors, it is embedded in the economic necessity, and the ecosystem has already shifted state. That is why this belongs inside the ocean of waste. Because water is not only a resource we drink, it is the working fluid of the economy. It enables scale, it absorbs what scale produces, then it transfers that imprint into rivers, deltas, and coastal seas. The economy treats that as normal operation. The ecosystem experiences it as a continuous pressure. And now I want to add the layer that matters most. Even if we accept that agriculture is needed, and energy is needed, and industry is needed, we still face the same structural gap. We don't manage this pressure as zones, we manage them as points. This is the same distortion I discussed and built into the ocean episode. On charts and in permits, offshore infrastructure looks like a symbol and coordinate and an object. But the real impact is never only the point, the real impact is the zone of influence. The same logic applies on land. A factory is a point on the map, a farm is a point on the map, a discharge pipe is a point on the map. But the influence spreads through a river basin, through an estuary, through a full bay, through coastal circulation. It can cover an entire coastline segment, it can reshape a whole delta system, and it can change the chemistry and biology of a semi enclosed sea. So, if we keep managing points, we keep missing the real geometry of risk. Because risk is not where the facility stands, risk is where its effects propagate. This is why global governance layer is missing. We need a shared way to mark zones of influence, not as political labels but as operational truth. A river basin that carries chronic nutrient load is a zone of influence. A delta receiving industrial chemistry is a zone of influence. A bay accumulating heat and residues is a zone of influence. And those zones should be visible not only to scientists, not only to regulators, visible in the way that shapes decisions. Because without official recognition, nothing can be managed at scale. If a zone is never named, it never becomes a governance object. If it never becomes a governance object, it never gets a strategy. And if it never gets a strategy, it keeps expanding quietly. And yes, acknowledging a zone is uncomfortable. It affects investment narratives, it affects the social license to operate, it forces a conversation about limits. But refusing to acknowledge it does not prevent the zone from growing. It only delays the moment when growth becomes undeniable. And there is one more absence that makes this even sharper. Even where people live inside zones of influence, there is almost no mechanism of compensation, not in money, not in control. If a business uses a river or coastal zone as a working component of production, then the system should demand built in compensation. Compensation means the environment is stabilized while it is being used. It means there are real buffers, not only paperwork. It means the load is monitored against thresholds that trigger change. It means reduction is mandatory when the system approaches limits. And it means alternatives are developed where pressure is too high. In other words, it means the economy does not only extract function from water, it carries responsibility for the condition of the system that makes that function possible. Right now, that responsibility is split into fragments. Monitoring is public and pressure is private and consequence is collective. And that is why we keep moving forward while the oceans keeps recording. You can hear this pattern even in small local stories. I recently spent time in France near the Allier River, and people there spoke about changes in the living system around them. Not as a theory, but as an observation. They spoke about biodiversity thinning out, about species pattern shifting, about a river that still looks like a river but behaves differently. That is what delayed feedback looks like. It is not a headline, it is a quiet transition. And if you don't have a governance system built around zones of influence, those transitions remain invisible until they become irreversible. This is why the ocean of waste is not only about pollution, it is about architecture. It is about the difference between a system that measures and a system that governs. It is about the difference between compliance and the ownership. It is about the difference between points on a map and zones of influence in reality. Because we keep describing water as a vital resource. We can keep publishing reports, we can keep funding measurements. But if the management loop remains broken, the outcome stays the same. The economy will keep using water as a technical tool. Water will keep returning altered. Rivers will keep carrying that alteration into the ocean. And the ocean will keep doing what our governance refuses to do. It will keep the record. Water does not become poison because something goes wrong. It becomes poison because it is used as a tool, returned as a residue, and managed as an afterthought. Agriculture, energy, and industry don't act outside the system, they are the system. What is missing is not data, not awareness, and not regulation on paper. What is missing is ownership of consequences that move beyond the point of use. Rivers carry what the economy leaves behind, deltas accumulate what cannot be seen upstream, the ocean receives the final balance. And as long as we treat water as a technical input rather than a shared system, the outcome will remain the same. The economy will keep functioning and the reports will keep being written, and the ocean will keep absorbing what no one claims responsibility for. This is not about blame, it's about design. Because systems don't fail loudly, they drift. And what drifts long enough eventually settles.